In our last video, we looked at aldol addition and condensation reactions, but today what we're going to do is we're going to practice that a little bit more, and I'm also going to throw in a few problems. So for our first practice problem, I want you to predict the products for the following. And like I said in my previous video, I'm a big fan of color coding everything. Makes it a little easier to figure out which molecules are going where. So I'm going to use an aldehyde drawn in red, and I'm going to react that with a second aldehyde that's different, shown in blue. So really the only difference between these is one of them has a methyl group, the other one has an ethyl group, right? And I'm going to throw these together in with some sodium hydroxide and water, and I'm going to keep the temp low or moderate temp, meaning I'm going to get the aldol addition reaction, not the condensation reaction where we kick off water. All right, so let's figure out what the product would be. And in this case, it is going to be a lot messier than we might first anticipate. And the reason for that is, let's say we have the red aldehyde acting as the nucleophile. Well, it could react with itself, right? So we could couple two of these red aldehydes together and get this as a product, right? So this new bond that I have in green is being formed between two of the red aldehydes. So that's statistically probable, right? Or we could have the red aldehyde act as a nucleophile and react with the blue aldehyde. And again, that would give us this product, which is going to be different than the product shown right above it. Or you could have the blue aldehyde act as the nucleophile and react with the red aldehyde, giving you, whoops, let me keep the colors the same, this beta hydroxyaldehyde. It looks like this. So really it's the same as above. We're just switching which aldehyde is acting as the nucleophile and which aldehyde's acting as the electrophile. But both are probable. And then last but not least, we could just have two of the blue aldehydes reacting with one another. And that would give us this product. So it's statistically possible that we could get 4 different products from this aldol addition reaction, which really emphasizes the points that when we do these reactions, it can be quite messy unless we're careful. So let's make a note of this. These are called crossed aldols. So crossed aldol reactions can be messy. But there are tricks to avoid getting all 4 of these products. So let's take a look at some of the tricks that we can do to avoid getting a complex mixture like we've got shown here. And the tricks are pretty straightforward. So the tricks to avoiding multiple products. All right, the first one is use reagents where only one aldehyde has alpha protons. So for example, let's consider this reaction with formaldehyde. Formaldehyde doesn't have any alpha protons because there's no alpha carbons to begin with. So if we were to react this with a second aldehyde, let's say this aldehyde, and we react this with sodium hydroxide and water, we're not going to have to worry about a mixture of products as much, right? In particular, because this is so electrophilic, if this is our nucleophile, it's very unlikely that it's going to react with itself. So if we do this reaction, what we're going to get is a really, really high concentration of our beta hydroxyaldehyde. We're not going to get a mixture of products. And like I said, That's due to the fact that this is such a good electrophile compared to our other aldehyde. So this is a good workaround, works in some situations. The second workaround is simply to use only one type of starting material. That's essentially what I showed in the last video. If you do an aldol reaction where you're only using one aldehyde, you're only going to get one product. So really that's not even an example of a cross aldol, but it avoids complicated reaction mixtures. All right, the third one I think is the coolest, and this one's going to be a bit different. It involves multiple steps. The first step is you want to drip your aldehyde or ketone into LDA. That's lithium diisopropyl amide. That's our really strong base. And if it's really strong, what that will do is form 100% enolate. Meaning we're not going to be under equilibrium conditions. All right, then what you want to do after that is add your second aldehyde to your enolate. And this can avoid getting this mixture of products, but it does require careful order of addition. You can't do things too quickly, and you typically have to keep things quite cold. So let's take a look at number 3 in action. And I want to do this using a practice problem. So let's say our goal is to make the following. So if I look over here, I can immediately see that, well, I've got my alpha position here next to my carbonyl, and I've got my beta position right here. And you might be saying, well, there's also an alpha position right here, but we can tell that that's probably not the alpha position that's doing any reactivity. We want to focus primarily on that alpha beta hydroxy combo, right? So what this means is that this bond right here must be our new bond, right? So I'm just going to label this. This must be our new bond. And when we kind of break this apart, we can say, well, if that's the case, then what this tells us is that this half, I'm going to highlight this kind of in heavy blue over here, must be one of our reagents, right? So if you're having trouble seeing that, I'll hash that up. And we'll say, all right, that means that the blue side on the left must have been our nucleophile, right? Because that's the carbon that must have attacked something else. And then over here, what we can do is we can say, well, that means that this half over here must have been our electrophile, because ultimately its oxygen became the aldehyde, right? So this is called retrosynthesis. We're just kind of working backwards. And then we could say, well, we could make this reagent by reacting our starting material with LDA. That's a really, really strong base. And it doesn't matter if it grabs this alpha proton or this alpha proton, it's going to give you the same product, right? So in this case, LDA would work quite well. All right, so let's do the full plan here. What we're going to do is we're going to start out with our original ketone. And like I said, this is actually the same as that. I just have one of the legs flipped up. And my first plan of attack is to react this with LDA. So I'm just going to put that as step 1. And then step 2 is to add in my second aldehyde. So what I mean by that is this aldehyde up here is going to be added into that enolate. So I'm actually going to list that as a reagent. So I'll go ahead and list that aldehyde next in my list. And then step 3 is to ensure that everything is protonated. We just want to quench this reaction with some sort of weak acid. Water is normally good enough. And by doing this, we're able to make our desired product. But like I said, the first thing I always do is I identify my alpha position, and then I identify the beta position with my hydroxy group. I identify that bond as being my new bond, and then I work backwards from there. So it's a really good way of kind of planning everything out. All right, so let's take a look at another practice one. And we're going to make the following. All right, what I want to do is I want to make this compound right here. And it's a little bit different than what we saw before, because in this example, we don't have a hydroxy group. However, I would still say that this is my alpha position, and this is my beta position. And we know that this is ultimately a new bond between two molecules. So let's kind of work backwards from here. And I'd say, well, to get here, we likely had an intermediate where there was a hydroxy group there. And this bond was a single bond. So then the question is, well, how can we get a double bond there? Well, if you remember, all you need for this is NaOH and heat. This is that condensation reaction. All right, and now what we want to do is we want to work back further and say, well, what pieces do we need here? Well, it looks to me like this would be one chunk. So I go ahead and say, well, this must have had a negative charge. Looks like that. And then on the other side, I'll just use purple. That must have been our electrophile, right? So in this case, it must have been something that looked like this. All right. So we've already identified which one's going to be our nucleophile and which one's going to be our electrophile. All right, so we could, if we wanted to, say, well, we can make this by treating it with LDA from our original aldehyde, and we could make that into our nucleophile. So let's draw out our plan really quick. All right, my plan, at least with the LDA method, was to first react this with LDA, whoops, to make my enolate. And then step 2 was to react this with benzaldehyde. And then step 3 is to react this with water. And by doing that, I should be able to get my final product. And I know some of you are probably asking, well, what about this last step with sodium hydroxide and heat? Well, in this case, we actually don't need sodium hydroxide and heat, because by doing that condensation reaction, we're actually able to extend the conjugation all the way through the ring system. So in this case, you don't really even need any additional heat, but this plan would work quite well. All right, I did want to show you that in this case, it's actually not even necessary to use LDA. Because if we think about our two starting materials, I'm going to box them really quick. We've got this starting material and this one right here. Only one of them has alpha protons. So this would be a good situation where you wouldn't necessarily have to do this. Another alternative route, if you wanted to get there, would just be to use NaOH OH, water, and heat, because only one of those reagents had alpha protons. All right, so that's where we're going to stop now. The problem of the day is going to be a little bit trickier, but I'll try to give you a hint to get you started. All right, good luck.